Hi everyone. I'm Fienny and I'd like to tell you about autonomous CNN, or AutoCNN in short. To gain a better understanding and appreciation of AutoCNN, let's get into a brief explanation of CNN. Convolutional neural network, or CNN in short, is neural network that use convolution in place of general matrix multiplication for processing data with grid-like topology. It is a widely used technique to solve image classification problem, speech recognition, and anomaly detection. Typically, high-performant classification network stacks multiple CNN layers on top of each other, followed by some classifier networks. Research had shown that the network depth, that is the number of CNN layer, and the network width, that is the number of kernel in each layer, both of them greatly affects the network accuracy. One general rule is that if the network is too shallow, it can't learn the features in the data well, thus leading to what is known as underfitting. On another extreme, if the network is too deep, it may contain way too many parameters that cause the problem of overfitting and vanishing gradient. Both the former and the latter extreme are not what we want in a CNN network, as it ended up to perform poorly on testing dataset. However, designing the right CNN architecture is hard and tiring. Firstly, it requires machine learning expert knowledge. Secondly, a network that works well on one problem may not work well on other problems. Thirdly, current methods that automatically generate CNN without human intervention take a lot of computation time and resources. It is thus less preferred for industry use. Therefore, due to the importance of CNN and the difficulty of designing a CNN architecture, this project proposed AutoCNN. It is a data-driven method to generate CNN network automatically for a given problem. This method is fast and computationally inexpensive. Moreover, the network generated by this method are highly immune to noise in the dataset and high performant. As shown in the flowchart below, there are 3 stages of AutoCNN. The first stage is called the CNN adaptation stage. This stage focused on evolving CNN layers to learn features as much as they can. The second stage is called the classifier optimization stage. Lastly, there is the all parameters optimization stage. Note that the transition among the stages are governed by the stopping criteria. As shown in the figure on the left, there are 2 main things happening in this stage. They are the CNN growing and kernel pruning. FSS is a short form of feature separability score, a measurement of how separable the spatial features are across different classes. C in the formula refers to the number of class, Fi denotes the average features from the last convolutional stage calculated over all the training data sample of the class I. High FSS indicates poor separability of features among different classes, while low FSS indicated highly discriminating spatial features. FSS performance is evaluated in terms of their exponentially weighted moving average, to avoid local oscillations. FSS saturation indicates the time to grow the convolutional stage. It happens when this condition is satisfied. Another thing that happens during the CNN adaptation stage is the filter pruning. Filter pruning strategy is implemented as it is hard to determine the number of filter needed at the start of the training. Filter pruning happens when the growing criteria is satisfied and there are kernel which are highly correlated. This correlation is measured using Pearson's product moment correlation. They are considered similar when they possess a strong positive correlation, that is when this condition is satisfied. Rho in the formula refers to the Pearson's correlation of the vectorized feature map of the filter pair Kp and Kq. Mu k and sigma k denotes the mean and standard deviation of all positively correlated filters of a given convolutional layer. The value 4 in the formula is motivated by the k-sigma rule, where k equals 4 indicates a 99% confidence level. If there is pair of filters that satisfy the criteria, the filter in the pair that has lower L1 norm will be pruned. After the CNN adaptation reached its stopping criteria, the classifier parameter optimization stage is started. In this stage, all the CNN parameters are frozen to avoid overfitting and speed up the training process. Only the weight of the fully connected layer is updated. Following that is the all parameter optimization stage. In this stage, all parameters are updated until it reaches the stopping criteria once again. The transformation among stages described before is governed by the stopping criteria. ETR, or the training error, is used to measure the network performance. However, the value of the training error may oscillate back and forth. To dampen the effect of such fluctuations, an exponentially weighted moving average of the error is used. The formula can be rewritten in this way, where the current training error has a weight of 1 over n. Moreover, stopping criteria is achieved when the following condition is satisfied. Alpha refers to the early stopping coefficient, W refers to the evaluation window, and MAN refers to the moving average of training error in epoch n. Max and min denotes the maximum and minimum observed moving average in the training error. Lower alpha value indicates higher tolerance to performance saturation, while higher alpha value indicates more conservative stopping criteria. The AutoCNN algorithm is tested on 6 different datasets. These datasets are selected carefully to test the performance of AutoCNN in different lights. AutoCNN managed to achieve the state-of-the-art performance on 2 of those datasets and ranked the second highest on another 2 datasets. In addition, AutoCNN takes less computing power and time compared to its peer autonomous generation algorithms. Moreover, the fact that AutoCNN achieved a high accuracy in misdrawn back image shows that AutoCNN network has high immunity towards noise. This is the AutoCNN demonstration website. To visualize the network, first, upload a training result file. After that, we shall see these graphs showing the network at a given epoch. The dark square refers to convolutional neuron, while the light square denotes the fully connected neuron. We can also play the animation to see how the network progresses through the training process. Done with the network visualization, now we're looking at the statistics during the training. These statistics are important as AutoCNN is data-driven, meaning that these statistics are the one that initiated action in the AutoCNN. As we can see, on several epochs before a new layer is added, the feature separability score had saturated. Once a layer is added, the error would jump, as the parameters in the latest layer are not yet trained. However, once it stabilizes, it should obtain an error that is lower than the previously saturated error before this last layer is added. Now that we have finished explaining about AutoCNN, the experiments, as well as the demonstration, it's time for the conclusion. Firstly, AutoCNN is a novel data-driven method to automatically build CNN networks. We had dived into the algorithm, which consisted of 3 consecutive stages, all of which are data-driven. Secondly, AutoCNN generated network performs well on the 6 datasets we used. This performance is achieved using significantly lesser computation resource and time compared to its peer competitors. Thirdly, due to its state-of-the-art performance on the missed variation dataset, we can conclude that AutoCNN generated network has high immunity towards the noise.